Hi. Today we're going to get started with the nuclear chemistry unit, which is the last unit in the New York State sequence for Regents level chemistry. So let's get started. There are a couple things we want to do to get into the unit. First, as a bit of a review, these are some terms you may have seen before, some symbols, and I just wanted to give everyone a chance to refresh themselves. Look at these names, these symbols, these numbers, and for each of these particles, how many protons, how many neutrons, and how many electrons are shown. And then based on what you see in the table, I want you to see what similarities there are between the two first entries, carbon 12 and carbon 13, and tell me why carbon is carbon, what makes an atom of carbon considered carbon. Feel free to pause if you need to. Go remind yourself, look back in your notes or your notebook. But I'm going to get started. So looking at the periodic table, the bottom number, bottom left-hand corner, is the atomic number. That's the number of protons. That's a 6 for carbon, a 6 for carbon, a 7 for nitrogen, and that's that lower number here for helium, so that's a 2. Since these are all atoms, we know they're electrically neutral, so if there's 6 protons, there's 6 electrons, and then we can fill in that chart. And then to figure out the number of neutrons, remember that this number here and this number in the top left corner of your symbol both mean the same thing. That's the mass number, which is equal to protons plus neutrons. So if this is a mass of 12 and there's 6 protons, there have to be 6 neutrons, 7 neutrons, 7 neutrons, and 2 protons. So looking at the data, I see two things that are the same between the two carbons, and I think by definition, the number of protons being 6 is what makes carbon carbon. And that's good to remember as we move on through this unit. A lot of what we've been talking about over the course of this year is actually going to pull back because we're going to focus on the nucleus, hence nuclear chemistry. So I think the number of protons will be far more impactful. This is a sample. Can I write on this image? Yes, I can. This is a sample of uranium. In a cloud chamber. And basically the way a cloud chamber works is that the black background is actually usually some sort of felt, and then you soak it with something like rubbing alcohol or acetone, propanone, and then you cool it down like a lot. The systems I've seen have used either a liquid nitrogen or a dry ice method of cooling, and the idea is you can cool down the liquid a lot without freezing it, and then as the liquid evaporates, the vapor layer gets very, very, very concentrated. So if I could draw this like rotated flat, we've got, block of ice underneath your fabric, and then you've got your little piece of uranium here. But at the same time, there's this like hazy cloud of alcohol or ketone. But it's vapor, so you can't see it. Now this particle is radioactive. And so therefore it's shooting off what we call radiation. And as the radiation flies by this cloud of alcohol, it actually produces a trail, a visible trail of condensation, and that's what you're seeing fly off of here. So there's a bunch of questions like what is radioactive, what is radiation, why is uranium radioactive? We're less concerned with the structure of the cloud chamber itself. I'll include a link in this video to the Electrobroom goes through this himself, so that's usually a fun video to watch, making the cloud chamber and how it works and what you can see. Some other things I can notice is that you can kind of see that some of the streams are going like this shorter distance, and then some are just like flying really far out there. And there's a big difference between those. The fact that this is a uranium sample, there's a lot to talk about. The other half of nuclear chemistry actually has a high historical background. There's a whole reading here about learning about transmutation, talking about the origins of chemistry. You can't forget about the alchemists. While the alchemists held a lot of beliefs that turned out, as far as we know, to be completely false. You can't turn a base metal into gold. You can't make the Philosopher's Stone. We have no such knowledge of an object. Sorry to Full Metal Alchemist fans. Sorry to Harry Potter fans. But those fall very heavily into the realm of fantasy or science fiction. That said, a lot of the properties and procedures that the alchemists develop end up getting used today. So like this image, and obviously artist rendering, but if you look at this setup, this looks suspiciously like a round bottom flask being heated over what could be very easily a fire. They didn't have Bunsen burners at the time. The methods and the lab practices that we use today, a lot of them were developed in the time of the alchemists, which you can see is about the 1600s. Hennig Brand is one of the more well-known ones. He decided that if a substance was gold colored, then it had gold in it, so he boiled down over 5,000 liters of urine. And then he also hoped to get a sorcerer's stone out of it, a philosopher's stone out of it. I don't know why. But while he obviously failed in that endeavor, he was able to isolate what we later determined to be phosphorus, which then, shows that science, a lot of times your failures can give very valuable information in addition to your successes. So transmutation, this idea here is changing anything into something else. So it's changing elements. And then why is it impossible to create? Because you can't do that. We can't do that as people. We can't just change an element because, like we said on the first slide, carbon's carbon because it has 6 protons in its nucleus. And if it didn't have 6 protons, it wouldn't be carbon. But how do you change the number of protons? Well, you can't just look at a chemical reaction and turn iron into calcium. At the very least, we know iron has 26 protons and calcium has 20 protons. And you can't just go in and rip out protons single-handedly. We don't have that technology at this point in human history. As far as we know, that doesn't exist. And so even if you were just to balance this for charge, it's not balanced for mass. The number of protons isn't right. I mean, maybe if we said 20 of these would make 26 of these, but I don't know. That's not really, we've never talked about that. In fact, one of the big things I probably said was you can't change elements into other elements in terms of your chemistry. And that's really the big line between nuclear chemistry and the rest of the unit, because now that's back on the table. We can actually change elements into, and when I say we, in nature, it has been observed that elements change into other elements in this select narrow band of processes. So for example, it is known that radium turns into radon by ejecting this helium nucleus particle. And this helium nucleus particle, that's going to be the thing we talked about. This is our radiation. So really, if we were to picture it, you have your concentric rings, right? And then here's your nucleus for your radium. And that's going to become radon. And through that process, the way it does that is a tiny little piece of the nucleus is also going to fly out of it. And that is the nuclear chemistry going on. We don't do it, really. I mean, okay, I'll talk about that later. But in this case, it just happens. Reactions where one element turns into another, we're just going to call, in general, a transmutation reaction. Anytime that happens. So that if one were to try and turn lead into gold, that would fall into that transmutation. A natural question to ask is, why do nuclei change at all? You and I are made of atoms, so are those atoms changing? And if yes, that's scary, and if no, I mean, why not, right? That's a fair number. That's a fair question to ask. So in the nucleus, we know protons and neutrons are found. And what we have on this graph here is we have a graph of the number of protons and the number of neutrons in a particle. So we remember in carbon-12, that's 6 and 6. In carbon-13, that would be 6 and 7. And in carbon-14, that'd be 6 and 8. And some things that we can glean from that is I know that carbon-14 is radioactive. It's used in radioactive dating for fossils and carbon-based organisms that have died, where carbon-12 and carbon-13 are not. So clearly there's something to do with that. Some nuclei are stable and some are unstable. And when they're unstable, they decay. And decay is just that process that we saw in the previous slide where they fall apart. If a nucleus is unstable, we call it a radioisotope. They emit the particle known as radiation. And the bulk material as a whole we would call radioactive. So if you had a big hunk of just carbon-14 atoms, I would call that a radioactive sample. Now that said, I said that we're all made of atoms, right? And so technically some of your atoms are carbon-12 and some of your atoms are carbon-13 and some of your atoms are actually carbon-14. So to a degree, you are radioactive. I mean, we're not talking like Hulk levels here, but there is some. As long as you're like eating food, you're eating some carbon-14, and as long as you're breathing out carbon dioxide, you're breathing out some amount of carbon-14. So a couple things to mention. This is, of course, Marie Curie and Henry, Henri Becquerel? I can't remember if that's how you spell his name. But these two scientists are both credited for discovering radiation around the same time. The unit was named after Becquerel. I believe the unit is BQ. And then the term radioactive or radiation or radioisotope, one of the terms, the whole idea of radio is credited to Marie Curie. Marie Curie being, of course, the only person to win Nobel Prizes in two fields, the only woman, definitely. But also of note is she did all this work, and we have all this information about nuclear chemistry. She died because of the work. I mean, what better image of a person doing work for the betterment of a species? Her lab notebooks, currently stored in lead boxes in France, are too radioactive to get near. You have to like sign waivers and wear protective equipment to even get to open the box to look at her notebooks, because that's how much radiation she exposed herself to, and that was before we knew it was bad. But there's a little bit of problem because they both kind of discovered it at the same time, and then there's a little bit of a story where it's like they tried to give more credit to him than her. I want to read up on the story at some point. For you guys, Table N from your reference table lists all of the nuclei that you need to know about that are considered radioisotopes. But on this graph, there's a couple things worth showing. So the line shown here, that's a 1-to-1 ratio. The black boxes all here, these are the ones that we call stable nuclides, which is the singular of isotope. And then all the ones that are colorful are not stable. The vast majority of particles are not stable in our universe. There's a very select few that are. And you'll see that for lighter ones, that is a 1-to-1 ratio seems to be a good thing. And then for the heavier ones, it's more like a 3-to-2 ratio of neutrons to protons. Something about bigger nuclei benefit from more protons. And you see that there are a number of methods to decay shown here too. Other things that you might notice is that there's a cap here, and that cap is at 82 protons. No stable... I'm going to write this over here. No stable nuclides heavier than lead. As the particles get heavier, something about the nucleus, it's like too big, and that's when bad things happen. Not bad things, when decay happens, when it's unstable. And lead is a nice line in the sand to keep in your head. Lead is the largest atom, the highest atomic number for which a stable nucleus exists. Beyond that, it doesn't. And actually, it's not that this graph keeps going. There's actually a void there on purpose. These are just the ones that we know about and the ones that exist and we've measured and are like stable enough to measure. And so there's some ideas, right? So this black line here is all the stable ones. Some people call it the band of stability. There's a hope that if we keep getting into heavier and heavier particles, eventually we will discover an island of stability where things suddenly become stable again. Hasn't happened yet. But above lead, you don't have any stable isotopes, and then no atoms in nature above uranium. So 82 and 92 stick in my head as, like, if you go into nature, you find uranium in nature. Anything that's on the periodic table further over doesn't really happen in nature because the particles are so big, so unstable, that they kind of fall apart in the last 4 to 15 billion years, and you don't find them in nature. So a couple words about radiation. For this course, we're going to focus on 4. We saw that there were several kinds on the previous graph shown here. I think that we got 6, but we're going to focus on 4: alpha, beta, gamma, and positron. Alpha shown in table O. These are the symbols that you're going to use in nuclear chemistry. Beta shown by there. These are the symbols shown right here. Gamma looks a little bit like a sideways alpha, and that's beta positive, which is a positron. So to talk about this really quickly, an alpha particle is a helium nucleus, no electrons. A beta particle is an electron. These are particles or energy emitted from a nucleus. That's basically what radiation is. Anything that's kicked out of an unstable nucleus in an attempt to move towards stability. And then gamma particles are interesting, and positrons are even more interesting still. So alpha is matter, it's an alpha particle. Beta is a matter, it's a particle, it's an electron. Gamma rays aren't really particles. Gamma rays are found on the electromagnetic spectrum, and gamma rays are just light. It's electromagnetic radiation. It's not visible, it's not X-rays, it's even more energy. You may have heard, obviously, colloquially, socially, gamma rays make you into the Hulk. It's not what happens. You expose yourself to too much gamma radiation, you get cancer, or you just die. It's not a good time. And then there's positrons, and sometimes positrons get released from nuclear matter, radioactive matter. There we go. And when we first got information about positrons, it was so weird. I should go find some pictures of this. A positron, if you look at the numbers, remember that the top number is the mass and the bottom number is the charge or the number of protons. So 4 and 2, right? Charge of 2, that's 2 protons. Charge of -1, that's 1 electron. A positron is a particle with no mass and a +1 charge. If I didn't know better, I would say that that was an electron, except for the part that is the fact that it's positive. A positron is an example of what we call antimatter. And the idea is there's balance in a lot of what we've seen in chemistry. Mass, charge, energy. There's a balance of matter. You can't create matter out of nothing. And so if matter is to be created, there has to be antimatter. And I don't really want to get into it. Like, I can give some supplemental readings, but there's a whole cliff that we're about to jump off in terms of content. The idea is that if a positron and an electron ever come together, they don't explode. They cancel out. The term is annihilate, where they cease to be matter and then become energy. It's not like you blow up a stick of dynamite and there's particles that fly anywhere. No, not particles, just energy. And so the matter cancels itself out. Now, there are tons of questions you're probably having about this. Chief among them, where is all the antimatter? That's a good question. We don't have an answer. We've hit about the limit. There's some hypotheses, some theories, but we don't know. All I want to say is when you're looking at table O, the top number is the mass, the bottom number is the charge, and you can figure out what these particles must be based on that information. So, when talking about radiation, if gamma radiation is so dangerous, we need to talk about PPE, actually, for lack of a better term. You may recognize the vest that this man is wearing. It looks suspiciously like the vest you might get if you go to the dentist and they take x-rays. That vest is very heavy. It's lined with lead. And the reason is, like we said, lead is the biggest nucleus that isn't itself radioactive. So the idea is that an alpha particle is, of the three, large. And so if we have a sheet of paper, you're actually going to block alpha radiation. So your skin blocks alpha radiation from your internal organs. That's actually one of the functions of skin. Beta particles are smaller, and there's this kind of relationship where it's the lighter it is, the faster it moves. There's a kinetic energy component to it. So it gets through paper, but you can block it with a sheet of aluminum. And this is why in a lot of materials that actually utilize radioactivity, you'll see a lot of aluminum or steel sheeting to shield the sample and to make sure the radiation only really travels where we want it to travel in the machine that we've built. You can also see that aluminum blocks lots of other kinds of radiation in terms of like electromagnetic radiation. I know if you have an easy pass, if you wrap it in aluminum, it doesn't get read. Like RFID tags don't get read if there's aluminum wrapped around it. When it comes to gamma, this is the lightest. It gets through paper, it gets through aluminum. Then if you have a block of lead, you'll see that some of it still gets through. So higher penetrating power requires more shielding. And that's basically the idea. There's a couple videos on the Periodic Videos channel where they go visit a nuclear chemistry lab and all the glass is green. And the reason it's green is they actually have put lead into the glass. Obviously the glass is there because you need to see what you're doing, but putting some lead in there is going to limit the exposure of radiation to you. The glass is also like 2, 3, 4 feet thick because obviously if you see through it, there's less lead than if it was solid lead. So in terms of, that's the background, but in terms of the execution of nuclear chemistry, in terms like the theory, the application, the actual chemistry side of things, we can write nuclear equations. So, and anytime you're getting asked about what type of decay does a certain particle undergo, I would say go straight to table N immediately because they actually tell you the decay mode, in which case you can go to table O if you need to, or if you know what it is. This is our alpha particle. You can write your alpha particle as the He, you can write it as the symbol alpha. We all understand it to be the same thing. In a nuclear equation, you have to follow all the same rules that we followed with any other equation. There is a conservation. So in this case, sum of top equals sum of top, and sum of bottom equals sum of bottom. Here's what I mean. In terms of the top numbers being mass, we know that the total mass represented on the reactants is 235, and the alpha particle represents 4 of that, so we know that the other particle has to have a mass of 231 atomic mass units. In terms of the bottom numbers, we know that the number of protons has to be conserved. So I know that we start with 92 with a particle of uranium, that's found in the periodic table. And then if 2 are kicked out as the alpha particle leaves the nucleus, what we're left with is a particle that has 90 protons. So really what we're talking about is we have a particle with a mass of 231 and a charge of 90, and so you look back at your periodic table, number 90 on the periodic table, I believe, is thorium. I don't actually, where's my periodic table? Oh no, I'm unprepared. Gotta record, we're recording, I have one right here. It's on my iPad. Yeah, 90 is thorium. The names get a little strange down at the bottom. But that's how we actually balance a nuclear equation. You just kind of count up the numbers on top, count up the numbers on bottom, and then find the appropriate symbol. This is, again, what we call a transmutation reaction, where we can see that as a result of this reaction, uranium atoms became thorium atoms. This means that back at the beginning, the animated GIF I showed you with the sample in the cloud chamber, if we let that uranium sit there long enough, and this is what's happening to some of the uranium atoms, eventually it won't be uranium anymore. And this is what I mean when I say no, you don't find particles above atomic number 92 in nature. When they do get formed in like star explosions and similar, they don't stick around over time. Now, the over time, we're not talking about half-life today, but the over time you can see, for this one we're talking about millions, hundreds of millions of years, so over time is a, variable term. It's a relative term. To look at tritium, which is the particle hydrogen-3, the isotopes of hydrogen are protium, protium for 1, deuterium for 2, and tritium for 3. Tritium is the one that's radioactive. Of the 3, protium and deuterium are not. And so we can use this information here and here to figure out what actually happens. So we know that this beta particle is emitted, and if we do our math, 3 equals 0 plus x, 1 equals negative 1 plus y, what we get is x equals 3, y equals 2. So 3, 2, and atomic number 2 on the periodic table should be helium. And so what happened is that hydrogen will decay through emission of a beta particle, and that's what that means, and you get helium. Now what's really strange about this, we're going to say this, I'm going to try and take this slow but not slow, because I realize I'm talking a lot. A particle of tritium is 1 proton and 2 neutrons, right? And a particle of helium-3 is 2 protons and 1 neutron. So really, to get from here to here, 1 neutron has to become 1 proton plus 1 electron. So interestingly, the beta decay happens in a nucleus where something happens and then an electron is kicked out, which there are no electrons in a nucleus. So you can imagine scientists' confusion when that was what was determined based on the data they have. And what we rationalize this to say is, not rationalize, our conclusion, which has been proven to be correct, is that when a neutron exists in or out of a nucleus, you can kind of think of a neutron, I mean, if you look at it, a proton is a particle with a charge of 1 and a mass of 1, and a neutron is a particle with a charge of 0 and a mass of 1. But when we got really specific, the mass of a neutron is like ever so slightly heavier than a mass of a proton, like 1/2000th heavier. A neutron is actually a proton and an electron fused together. And if you think about it, if you take a proton and an electron, you jam them together into one particle, you mix them, you get a particle with a mass of 1 and a charge of 0. So, yeah. The reverse of that is what happens under beta decay. You can get the opposite of beta decay, where you do electron capture, where a proton becomes a neutron. And actually, if you have a proton or a neutron outside of a nucleus, over time it actually does decay into a proton and an electron that's slightly more stable outside of a nucleus. So that's the weird thing about that. But the short answer is helium-3 is the particle that gets decayed, that gets produced by the decay of tritium. Neon-19. Atomic number 10. They're saying here on table N that it undergoes positron decay. And you can show the E or the beta, either one's fine. So 19 equals 0 plus x, 10 equals 1 plus y, y equals 9, x equals 19, 9, 19, so that's fluorine. Now, similar to the beta decay, positrons are antimatter. There's no antimatter in matter. And so there's a couple ways to look at this, but basically what ends up happening is that 1 proton becomes 1 neutron. And so the idea, I think, is that you create a positron-electron pair. The electron falls into a proton, makes a neutron, and the electron, or the positron, just yeets out of there. There's, how do I put this? There's observational data to say that it happens, and then we as scientists try to understand the connective tissue. And so, like, any way you make sense of it is how it works. Just make sure that your top numbers and your bottom numbers are all adding up to what they need to. Proton decays into a neutron and a positron, which leaves. That's another way to think about it. So looking at this equation, you can also be asked to say, given an equation, what's the missing particle? So instead of saying, I know it's beta, what gets made, you can say, thorium becomes praseodymium. Protactinium. I always confuse those two. Protactinium. And so what particle is released? And we can play the same game. 239 equals 239 plus x. and 90 equals 91 plus y, y equals -1, x equals 0. So we've got a particle with 0 and a -1, and that to me sounds like a beta particle. I can't remember if thorium-239 is on table N for you to check, but of course, you know, you can check online to see if that's a valid decay mode. Or you have your math. If this is what's happening, that's what happened. There's one more thing to mention before I cut the line today. Everything we've talked about in terms of today is natural transmutation. And the idea is that one particle will spontaneously, because it's unstable, fall apart into a piece of radiation, a radioactive particle that we know about, a radiation particle, or a gamma ray, and then some other nuclide. This is what we call decay, also known as natural transmutation. Natural because it is not initiated by anything. An artificial transmutation would be a case where you have a nucleus and you actually shoot another particle at it. The new particle hits your nucleus, sticks together, becomes something unstable, and falls apart. So the biggest thing to note is that in a decay, you have one reactant. And for an artificial transmutation, otherwise known as bombardment, you've got 2+ reactants. So looking at a question that you might see on a test or a quiz to say which one represents natural transmutation, note that in 3 of the 4 choices, there are 2 reactants. So here are some examples of what artificial transmutation would look like. But number 4, just by chance I picked that one again, is the example of natural transmutation. It might seem like anything's possible if you look at it that way. I can just jam any particle into any particle, and actually, yeah, you're right. And could you make anything out of that? I mean, yes. Can you do anything? Yes. Given the right technology, given the right machinery, and the right resources, yeah, of course. The thing to remember that on this graph is we've done it already. We've looked at all of the isotopes that are feasibly possible to make, and you can see that the vast majority of them, if made, are unstable and will fall apart on their own through decay into something else. I think there might even be more than this. I don't know how exhaustive this list is, but as we get further away from that line of stability, the particles get so unstable that even if you were to make them, they exist for milliseconds or microseconds or nanoseconds, and so you can't even measure that you've made them, and it's just kind of an explosion. But hopefully that's a nice introduction to nuclear chemistry. I've used the word nuclear and explosion and radiation, and I think I worked with the Hulk in there and thorium. So that's a nice foundation on which to move forward. Thanks for watching.